Hey everybody, it's Mr. Woodward. Let's talk about fundamentals of circular motion. We're going to look at 4 examples of objects moving in a circle and try to identify the forces involved, the velocity, and the acceleration. So taking a look at the top here, from looping roller coasters and racetrack turns to tetherball and orbiting planets, circular motion is all around us. That's a bad joke. Each of the following scenarios depicts a real-life example of circular motion. So for each scenario, I want you to do 5 things. First, draw a free body diagram of the object in top view or the side, whichever is more helpful. Number 2, identify the force or forces responsible for pushing or pulling the object into circular motion. This is called the centripetal force. As a reminder, centripetal means pointing towards the center of the circle. Number 3, identify the directions of the object's velocity and acceleration while it's moving in a circle. Number 4, calculate the object's velocity. Since the object is moving in a circle, it will trace out a circumference, right? So 2 pi r is the circumference of a circle. Therefore, the velocity would be the distance, 2 pi r, over the time. Therefore, you get 2 pi r over t. Number 5, calculate the object's centripetal acceleration. And here's the equation that we will use for centripetal acceleration. Velocity squared divided by the radius. Again, centripetal acceleration means an acceleration that is pointed towards the center of the circle. Okay, let's take a look at this first example here. At the top of a roller coaster loop, of radius 14 meters. So we're gonna focus on this roller coaster car right here that's at the top, and ask ourselves, what is true of the forces and the motion of that rider who's like at the front? So we're assuming the rider's going this way around the loop. What's true of that car at the front of that roller coaster train? Okay, so first, let's draw the velocity and the acceleration vectors. So we're focusing on this car at the top. And the velocity, first of all, so I mentioned we want to pretend that the car is going this way around, right? So at this particular moment, the car is going that way. That is the direction of its velocity. And how do I know that? Because we've seen from others' demonstrations that if the car sort of fell out of the loop, or if the roller coaster track were to disappear at that particular instant, the roller coaster car wouldn't go out like this, it wouldn't go out like this, it would go off in a straight line because of Newton's first law, right? In the absence of a net force, objects will move in a straight line at constant speed. That's ignoring gravity, of course. So just focusing on the motion of the roller coaster car by itself. Eventually gravity would take over and it would, of course, move down like this. But at this particular moment in time, the velocity is straight forward. All right, what about the direction of the acceleration? Well, we know, if you saw my demonstration before with a tub of water that was spinning, the acceleration is always centripetal. So that would be towards the center of the loop, which means this way, okay? Notice that velocity and acceleration in this example are perpendicular to each other, okay? You will see that again. Let's keep going on. Draw a free body diagram of that particular roller coaster car, labeling all the forces. So at this moment, right, we've got the car at the top of the loop, and the loop is here, but I'm going to erase that because it's not part of the free body diagram. And I'm going to consider just the forces acting on the car at that moment. Gravity is always present, so we can go ahead and draw that downwards, okay? But there's another force, and it's the force on the car from the roller coaster track, okay? That track is above the car at that moment, and so the track is actually pushing downwards on the car. So gravity and the normal force are both pointing in the same direction. Next, which force or forces are centripetal, meaning pointing towards the center of that loop? Well, there's actually 2 centripetal forces. There's the normal force and gravity. And in fact, the sum of them in this case is going to be considered the centripetal force. Next, let's calculate the velocity. If one loop takes 3 seconds, Okay, so that's the time to travel that whole circumference. Well, the velocity is always the distance over time. This is a really kind of elementary definition of velocity. Velocity is the distance over time. And the distance is going to be the circumference of the circle. So the distance is 2 pi r, and the time we'll call t. Okay? Well, we actually know the radius and the time. The radius is over here. We were told that the radius of the loop is 14 meters. So let's put that in, 14 meters. And we know the time is here. It says one loop takes 3 seconds. Okay? So I'm going to put 3 seconds here. Okay, multiplying that out, I get 29.3 meters per second as my velocity. Finally, calculate the centripetal acceleration. Okay, so we just found this velocity. Now we want to find this acceleration. Okay, well, the acceleration in the centripetal direction is v squared over r. We know the velocity, we just found it. It's 29.3 meters per second. I'm going to square that and divide by the radius of 14 meters. And I get 61.3 meters per second squared. Now, if you compare that acceleration to free fall acceleration, which is 9.8 meters per second squared, this is about 6 times larger than that. So we would say that the roller coaster was in a 6G loop, which is a lot of acceleration. And in fact, this is probably an unsafe roller coaster. That level of acceleration, that number of G's, would be way too high for the average person to withstand without passing out. So this is a little bit of an unrealistic problem in that sense. Let's keep going. Let's try number 2 on a merry-go-round. Okay, so now we're in top view. We're looking down at this girl who's holding on to this bar and is sitting on the rotating platform of the merry-go-round. And we want to start with the velocity and the acceleration vectors. If this girl is traveling counterclockwise in top view, meaning this way. Okay, so here's, I'm going to put the girl here on the merry-go-round. Actually, I'm going to make it just a little bit more obvious here, so she's on the circular path itself. At this particular moment, her velocity is this way, right? That's the way she's facing. And that's the way that she will move if she were to fly off the merry-go-round. And then her acceleration is centripetal, so it's this way. And again, those are at right angles to each other. Okay? Now, let's flip our view and think inside view. If we could see the girl inside view, here she is. She's sort of sitting, that's her hair, sitting on the merry-go-round. Here's the bottom of it. And we're going to ignore the bar that she's holding on to just sort of simplify the situation, because this would still work if she wasn't holding onto the bar, if she was simply sitting on the merry-go-round. Okay, what forces would be acting on her? Well, there would, of course, be gravity pulling her down. There would be a normal force from the rotating platform of the merry-go-round. But something must be pulling her into a circle. And it's got to be her interaction with the merry-go-round platform itself, right? And the thing that's holding her into a circle is friction. So there's this frictional force. And actually, I suppose if this is her face, friction would be the other way because of the way that she's rotating in the picture. But the point is it's sideways, right? And specifically, it's static friction. As a reminder, static friction is friction while gripping. Kinetic friction is friction while sliding. So static friction is holding this girl onto the platform and actually causing her to turn. So which force is the centripetal force? It's this friction. And again, I mentioned it's specifically static friction. Now, what's her velocity if one rotation takes 2 seconds? we can go back to her velocity is the distance she travels around a circle, which is 2 pi r, divided by the time it takes. The radius is over here. It's a 3-meter radius merry-go-round. So we're going to put that in here. And then the time is 2 seconds. So the 2's, of course, would cancel out, and her velocity is just 3 pi, which is 9.42 meters per second. And her centripetal acceleration, velocity squared divided by the radius. So we're going to take her 9.42 meters per second, square it, divide it by the radius of 3 meters. And her acceleration is 29.6 meters per second squared. Again, comparing that to free fall acceleration, which is 9.8 meters per second squared, she is now pulling about 3 Gs, which is much more realistic of a survivable rate of acceleration.